Welcome to Hic sunt Dragon, here be dragons. I keep hearing people say really stupid things, normally in regards to basic nuclear physics and radiation. So, it seems obvious that I need to make a refresher course, or even an intro to nuclear physics course, for those that just never paid attention in school, like you. Right there, stop looking at other tabs and get back over here. No, that tab. Yes, that tab. Click it. Right, okay, welcome back. Now take your hands off the mouse. No, off the mouse. Okay, good. Okay. Now, you might remember this, or you might not, like you. Atoms are composed of a proton, a neutron, and an electron, though only the proton is absolutely required. Electrons, which don't really spin around the nucleus of an atom like a spaceship in orbit, are fermions, which aren't made of anything else. They are a fundamental particle with a negative charge. Another fundamental particle is the quark. In simplest terms possible, a quark is what protons and neutrons are made of. They are categorized by the charge, or spin. An up quark has a positive spin, and a down quark is negative. It's actually incredibly more complex than that, but this will do for now. Protons are made up of two up quarks and one down quark. Neutrons are made up of one up quark and two down quarks. The proton. Protons are positively charged. The number of protons determines the element. If you have one proton, you have hydrogen. If you have two protons, you have helium. It doesn't matter where you are in the universe. Two protons is two protons, which means it's helium in every galaxy. So stop saying that different galaxies have different elements with different properties. They don't. The electron. Each atom has about the same number of electrons as protons, depending on charge. Adding or removing an electron determines the charge of the atom, as in negative, neutral, or positive. This is something we'll get into a lot later. Now, neutrons. The number of neutrons affects the properties of the element, and an element with a different amount of neutrons is called an isotope. Isotopes can have different properties than the base element. Now, here's the thing about atoms. Atoms always want to be as stable as possible. So they want to have the same amount of protons and neutrons and electrons. But mostly protons and neutrons. When the number of neutrons is not the same, we've got an isotope, which is radioactive. Now let's look at the simplest atom, hydrogen. One proton, one electron. Let's add a neutron, and now we have deuterium. But let's add another neutron, and now we've got tritium. And tritium is radioactive because it has one too many neutrons. Now, in order to improve stability, an atom goes through what is called beta decay. This is the process in which a neutron can become a proton, where neutrons transform themselves into protons by emitting an electron. Essentially, they shed a negative charge to become positively charged. Now, an antineutrino is also released during this process. So, this converts the down quark to an up quark, giving us proton. That electron that's flung off at high speeds like a tiny little bullet is called beta radiation. And that antineutrino, if we could catch it before it goes poof, is how we can get antimatter. But it's not the only way. It's not something we're even going to discuss right now. So the electron is tiny and fast, like a little BB gun. A piece of paper can stop it. Your clothes can stop it. Your skin can stop it. In fact, even the atmosphere stops it pretty quickly. But should it actually get inside of you, then you have issues. And you can essentially get an internal sunburn, which is ouchy. But it's not the end of the world. So, let's look at the radioactive isotope of hydrogen known as tritium. Tritium has a half-life of 12.3 years. So, every 12.3 years, half of the tritium will become helium, specifically the helium-3 isotope, as we still have a neutron. But there's now two protons. This is why tritium nightlights such as gun sights, emergency exit signs, and etc., keep dimming over time. The glow they give is due to beta radiation from tritium. It stops once it's no longer tritium and becomes helium. So now, let's look at a really, really radioactive element. We all know it, and we all love it. Welcome, uranium, with 92 protons and 146 neutrons. Now, what did we learn earlier? Neutrons make isotopes, making this the uranium-238 isotope. We also learned that atoms love equality and stability. And this has too many neutrons. It is really, really unstable. Due to it being so unstable, uranium emits what are called alpha particles, or alpha radiation. And an alpha particle is actually several particles. It's 2 neutrons and 2 protons. Wait, that's just helium without the electrons. Yep. Alpha particles are really big, but really slow. You can still stop them with paper, clothes, even skin. But wait, they have no electrons. So what happens if you eat one? Well, the alpha particles are going to steal electrons from you, which isn't that great. But once they're inside of you, they can then bombard your innards with not these little tiny BBs like beta radiation, but more like 50 caliber BMG ammo, which does a lot more damage. But again, you're still completely safe as long as you keep them outside of you. Now, some isotopes are so unstable due to the amount of neutrons, like uranium-235, which is just like uranium-238, but it's missing 3 neutrons, which puts it right on the edge of stability. So that when it does absorb another neutron, it actually splits itself apart into 2 separate elements, barium-141 and krypton-92. This is called nuclear fission. Now, when this uranium atom splits, it releases a lot of heat, several neutrons, known as neutron radiation, and a high-energy particle, similar to an X-ray, known as gamma radiation. Now, we have our 4 types of radiation. Alpha, which is an helium atom with no electrons. Beta, which is a high-speed electron. Neutron, which is, well, a neutron. And gamma, which is very similar to an X-ray. Now, we know U-235 splits when it gets a neutron. And when it splits, it releases 3 neutrons in the vicinity of more U-235, which of course is going to hit those nearby U-235 atoms, causing each of them to split and release more neutrons and heat. You see where this is going? Now, if you could find a material that would, say, absorb neutrons, then you can actually stick it into the U-235 and actually reduce or stop the reaction, or even speed it back up by pulling it out. And this lets you create a lot of heat without a runaway reaction overheating the container you have it in. You can then use that heat to make steam, which can then drive a turbine to make electricity. And we've got a nuclear reactor. But what if you can find a material that's able to reflect neutrons, like a mirror? So instead of absorbing them, it reflects them back towards the U-235. Well, then that reaction can get really going and even go out of control. And then you've got a fission bomb. Boom, boom. Now I'm going to stop here so you can go soak your head in some cold water and recover. Now if you want to know more and want me to continue on with the series about nuclear physics, let me know, leave a comment and subscribe, and I'll do it. And if it hurts too much, just let me know and we can move on to something else. Anyways, have a great day.